So this is problem number 6. It's from the 2009 BC exam, Form B. And typically number 6 is going to be a question involving series. And this is obviously no different. They start us off by saying F is defined by a power series here. So they give us the sigma notation version of the power, or excuse me, the expanded notation version of the power series. And then here would be the sigma notation representation for it. In part A, they want us to find the interval of convergence of the power series and then justify our answer. So what you typically would do if you're asked to find the interval of convergence for a power series is you typically go right into the ratio test. And so that's what I have begun over here. Now, I kind of thought ahead and I said, well, if I'm going to apply the ratio test, I'm going to have to individually consider the cases when the ratio test is inconclusive. And the ratio test is inconclusive when this limit is equal to 1. And so we'd have two things to consider because of these absolute values. We'd have to do a little bit of extra work at the tail end of this, and sometimes that work can get a little bit lengthy. The thing that I noticed was that this particular series is geometric in nature. You know, we have a coefficient out here, and then we have a base raised to a power that's represented by the index. So this series fits our geometric series definition, and we know a geometric series is going to converge to A, the number that's out in front of the base, over 1 minus r is referred to as the base. And it's going to converge to that if the absolute value of r is less than 1. Well, r would be represented by this base right here, just x plus 1. So I am going to go this route rather than the ratio test route, only because this is going to be a lot quicker to get to the end result. So if we go ahead and take this ratio, x plus 1, that base, toss it in absolute values, and try to figure out when that's less than 1, we're going to have to figure out when this quantity, x plus 1, is less than 1, and when this quantity is greater than negative 1. And if you solve both of those inequalities, subtract 1 on both sides of this one, subtract 1 on both sides of this one, you get x is less than 0 and x is greater than negative 2. So as a single inequality, that could be represented like this. So there's your interval of convergence. I did specify the radius of convergence as well, although when I was rereading the problem, I don't really think it asked us to do that, right? Yeah, it just wanted the interval of convergence. So the interval of convergence is negative 2 to 0, not including either endpoint. And the reason why is because we're using the definition of a geometric series to determine that result. When we look at Part B wants us to find what the sum of the series represented here actually is. And working off of what we said a few minutes ago in Part A, we said that this series is geometric. The A value, the coefficient of the base, is 1, and the R value, the base itself, is x plus 1. And our series is going to converge to A over 1 minus R for the x values that we specified in Part A. And what is A over 1 minus R in this case? Well, 1 over 1 minus R. Be careful with that set of grouping symbols. That's something that, if overlooked, can get you the wrong value or the wrong function that this series converges to. So when you distribute that negative in, you're looking at this, and the function f is going to be 1 over negative x. Now, that does only hold for the x values between negative 2 and 0. It only holds for the interval of convergence of this power series. But this series converges to this function, or has this function as its sum, when x ranges between these two values. In Part C, what they ask us to do is they ask us to take this new function, g of x. So g is defined as a definite integral. The variable is in the upper limit of integration. And then the function f is the integrand here. What we want to do is we want to find the value of g of negative 1, or explain why it can't be determined. So, excuse me, negative 1/2. So when you evaluate a function, your best bet is to just put negative 1/2 in place of the x's. So that's all I did. Now, what I remembered from Part B was what function f actually was. Because this interval, negative 1 to negative 1/2, is enclosed within the interval of convergence, rather than using the series for f, since the series converges to the function from Part B, negative 1 over x, what we can do is we can re-represent f of t with what it converges to, because we are within the interval of convergence of the power series. So I'm not using negative 1 over x because the variable that's within f here is t. So I just swapped out the x in f for a t. So I put negative 1 over t in place of f of t. What is the antiderivative of negative 1 over t? Well, it's going to be negative natural log of the absolute value of t. The absolute values definitely are crucial here because you're going to be putting negatives in place of those t's, and the absolute values are going to be necessary in order to get you to the point where you have positives within your logarithms. So this ends up being negative natural log of 1/2, and then plus the natural log of 1, and it's plus because we would be subtracting a negative there. The natural log of 1, when you do the absolute values of this, is 0, so that piece drops off. So I get this as the result, which would be an acceptable result. Now, the one thing that you might question if you look at the solutions on the College Board is the fact that they have the natural log of 2 as the value of g of negative 1/2. And you can go ahead and try to simplify this a little bit. Whenever you have a quotient within a logarithm, you can break that up into the difference of two separate logarithms. So that's a property of logarithms that you've used a handful of times. And you're going to have the logarithm of what you have in the numerator minus the logarithm of what you have in the denominator. And the reason why it's kind of nice and beneficial to do that here is because of what we have in that numerator. The natural log of 1 is going to become a 0, and then that piece drops off. And then if you distribute this negative, that was the coefficient of the outside logarithm. If you distribute that into this second term, that'll give you positive natural log of 2 as your final answer, which is a little bit nicer result than what we have specified up here. But they're equivalent, and both would be accepted. But this is what you're going to see on the College Board's solution page. And then the last part of this, part D, defines a new function h. H is dependent on the function f. So we're just creating h by putting x squared minus 1 in place of the x's in f. We want to find the first three non-zero terms in the general term for the Taylor series for h about 0, and then find the value of h of 1/2. Now, the really long way to do this would be to try and use the definition of a Taylor series and try and determine that from the ground up. The nice thing here, since we have this series representation for f, check out what happens if we put x squared minus 1 in place of all of these x's in the series for f. What we end up having happen is that you have a minus 1 that goes in with the way h is defined, and then the series representation for f has all these plus 1s. So those are going to cancel, and what you end up with is you end up with a series that is based at 0. So the series for f is based at -1. The series for h has to be based at 0. Coincidentally, by putting this quantity in place of the x's in f, we end up with a new series that is based at 0. So here's the Taylor series for h that is based at 0. If you simplify each of these individual pieces, I guess it only asked for 3, and I kind of represented the first 4 non-zero terms there, but if you have extra, that's fine. You just want to make sure you have the required amount, at least the required amount. And then I did simplify each individual term, right? This is x squared squared, so that became an x to the 4th. X squared to the n becomes x to the 2n. So here's the series for h of x, and it is based at 0. And then in the second part of this is kind of weird, and if you didn't really know where to take this, it might kind of throw you off initially. The second part of part D doesn't depend at all on the series that we wrote down for the first part of part D. They ask us to evaluate h of 1/2. So if you're evaluating h of 1/2, just take the definition of h here. Put 1/2 in place of this x. What happens? Well, you get 1/2 squared minus 1. 1/2 squared is 1/4. Minus 1 takes you to -3/4. What's f of -3/4? Well, you could either try to use the series to find that out, or since this x value that's in f, this is an x that's going into f, this input for f, this is within the interval of convergence that we specified in part A and part B, right? -1/4 is part of that interval of convergence. So rather than using the series definition for f, since we are going to converge to that function that we specified back in part B, 1 over -x or -1 over x, what we can do is we can just evaluate this function at this x. And we're going to end up with the negative from the definition of this function f converges to on its interval of convergence with -3/4 tossed in place of this x. and the minus and negative gives you a positive result. Rather than dividing, multiply by the reciprocal, and you have your result.